Let's see this question. We want to find the equation of a line parallel to this plane, right? Because we have x, y, z to the power 1. So we know this is representation of a plane. So let's draw a plane. So here the coefficient of x, y, z, the coefficient of x, which is 1. So we know that represents a normal vector, right? So 1, comma 2, comma -3. That represents the normal vector to this plane, which means any vector on the plane will be orthogonal to this vector. And this line we're looking for is parallel to this plane. So let me draw with the blue color. It's parallel to this plane. It doesn't have to go this way, just for easier to see it, right? And this line, actually, we don't really care about the direction. We only care about the representation of the line, which means it could go this way or could go that way, the vector. So because it's parallel to this plane, so if we extend the normal vector, right? So this normal vector will be orthogonal to this vector as well, to this line as well. So we're going to use that feature and also use this normal vector to write the representation of this equation for the line. So what do? First, let's say the given point is somewhere here, 1, 2, 1, right? We're given this point. And there are some x, y, z, or x, y on this line, but let's just see z on this plane, right? Which is parallel, which is orthogonal to this normal vector as well. So now we know two orthogonal vectors. When we do dot product, we get 0. So that means 1, 2, -3 dot product with this vector, which this vector will be x minus 1, y minus 2, z minus 1. Because we have these 2 points, we subtract, then we'll get a vector. So which is x minus 1, y minus 2, z minus 1. And when we do dot product, because they are orthogonal to each other, so the dot product is 0. So when we do dot product, what do? We multiply component-wise, 1 times x minus 1, which is x minus 1. Then we do plus 2 times y minus 2. So we multiply component-wise, then we add them. Then add -3, which is subtract 3 times z minus 1. And that gives us 0. So simplify this, we get x minus 1 plus 2y minus 4 minus 3z plus 3, that's 0. Or simplify, we get x plus 2y minus 3z equals -1, -4, that's -5. -5 plus 3, -2. -2 move to the other side, get a 2. So see, this is a plane. This is a representation of this plane, right? It's parallel to this. Now we have this plane. And this line we're looking for, of course, is line on this plane. So what do? We're going to use, let's see this, we're going to find a vector, which is dot product with this normal vector to be 0, which we use 1, 2, -3, this normal vector again, dot product with a vector, and that dot product is 0. So if we, so -3 times 1 would be -3, then you times -1, you times 1, 1 times 1 is 1, 2 times 1 is 2, right? Pass through 3, then plus -3, that would be 0. So we can use this one, where you can find infinitely many of them, right? So for me to find this one and use this one. And this one, so I'm going to treat this one as my direction vector for this. So remember the line representation of t in three-dimensional space. Here's the initial vector, 1.21, plus, well, direction vector, right? So I'm going to subtract those two. So I'm going to t times, I'm going to subtract 1 from 1, I get 0. 1 subtract 2, I get negative 1. Then 1 minus 1, that would be 0. I simplify this one, I get t times 0, which is 0. So 1 plus 0, which is 1. Then t times negative 1, negative t. So 2 plus negative t, that's 2 minus t. Then t times 0, that's 0. And that's it. Now 1 plus 0, 1. By t times 0 is 0, 0 plus 1, then 1. So the vector. But in three space or in higher space, other than two-dimensional space, we use a vector to be a presentation of a line. So in this case, it's 1, comma, 2 minus t, comma, 1.